All right, guys, welcome back to our continuing discussion of this really important central pathway um, at the core of intermediary metabolism. That is, of course, the TCA cycle. And last time, I sort of gave you an introduction, an overview of this process. Excuse me, and we started talking about the very first key reaction, right? I pointed out that the TCA cycle is really the pathway that organisms, all organisms that have access to molecular oxygen will run when they want maximum energetic benefit. And they will burn anything they possibly can through the TCA cycle that can be converted either into pyruvate, acetyl-CoA, or certain other dicarboxylic acids. And this is the way in which you get the maximum energy benefit available from the carbon backbones of those molecules, right? So because we've been talking about glucose metabolism and the breakdown of carbohydrates, we sort of began our discussion of the TCA cycle at that entry point, right? Specifically, as we came out of glycolysis to pyruvate, right? We considered that first step of what I call the sort of first phase of the TCA cycle, the way I like to organize it, into the formation of acetyl-CoA, right? And this is what we saw last time in that the pyruvate dehydrogenase complex, as you recall. And of course, this pathway, if you recall, generates some significant amount of, or generates as a key part of this oxidative decarboxylation. It creates some NADH, right? And it also decarboxylates that pyruvate, kicking off that CO2 group to form acetyl-CoA. And I pointed out how the beginning of this reaction very much looks like pyruvate decarboxylase that we saw in alcoholic fermentation. But then we preserve the free energy available rather than just dumping those electrons from GAPDH in this thioester bond, right? Okay, so the trick now is how do we use that activated 2-carbon carrier, that acetyl group, to now run this sort of subsequent set of reactions of the TCA cycle. And I pointed out, and I find this helpful to sort of think about this in different levels of detail. And so I'm just going to remind you of that high level of detail. If you recall, this is, of course, a 2-carbon unit in that acetyl group, right? And the next thing we're going to do, right, is we're going to condense that acetyl group with oxaloacetate, that dicarboxylic acid oxaloacetate, right, to generate then this 6-carbon tricarboxylic acid citrate, right? All right, so if oxaloacetate then is a C4 unit, and we're going to condense acetyl-CoA with it to then generate a C6 unit, right? And then we're going to take this guy and we're going to run through what I call sort of phase 2 of the cycle. If this is sort of the pyruvate dehydrogenase complex, if this is what I call sort of phase 1, right? Phase 2 is this process of creating citrate and then running it through the first half of the TCA cycle down here to create succinyl-CoA, right? So we kind of start the cycle with a thioester and we get halfway around by creating another thioester. And in the process, we throw off more CO2 and we create more NADH, right? Okay, and that's sort of phase 2. That's what we're going to talk about in the video today. Then in the subsequent video, the name of the game is how do we take the succinyl-CoA, which is now, again, a C4 carbon backbone, and turn it back into oxaloacetate so the cycle can continue. And this is where we're going to actually create a little ATP, our 1 substrate level phosphorylation, and we're going to throw off a bunch more NADH and FADH2, right? Okay, so big picture reminder of where we are So, but today, what we're going to do is we're going to come through this part of the cycle right around here, right? Okay, so first part of this is we're going to start right here at this condensation reaction where we put oxaloacetate and citrate back together, right? All right, so let's just dive right in to this process, to what I'm going to call reaction 2 of the TCA cycle, or the citric acid cycle. All right. All right. So like I said, reaction 2, in detail, we're going to take acetyl-CoA, right? And I'm going to write out this methyl group now a little more explicitly, because we're gonna need to think about that a little bit. Like I've been using the sort of shorthand convention of just leaving the methyl group off, that line terminating that way and assumed to be a methyl group, but I'm going to put it in here explicitly, right? And one of the things I want you guys to do is keep your eyeballs on our 2 carbons that are coming in here from acetyl-CoA. All right, like I said, now we're going to condense this guy with this 4-carbon dicarboxylic acid, oxaloacetate. All right, so if this is acetyl-CoA, and this is oxaloacetate, right? And we're going to need a little water for this reaction to go, right? And we're going to create this 6-carbon tricarboxylic acid citrate, right? OH, COO minus, right? So this is, let me tell you what, let me write that out a little bit more, space that out. I'm cramming that up here, so let me space that out a little bit more. It's not as crammed up. Right. Okay, citrate. Now, like I said, keep your eyes on those 2 carbons that were coming in from acetyl-CoA. Those 2 carbons are going to be right over here, right? All right. So also, let me just go ahead and write down, our other products here. Because we've used that acetyl group, that activated 2-carbon group. This is also going to then generate, this reaction will yield some reduced CoA and a proton, right? The enzyme that drives this reaction is, of course, citrate synthase. Super important enzyme right here at the entry to the main part of the TCA cycle. Free energy of this reaction is quite favorable. Delta G naught prime for this reaction is like minus 32 kilojoules per mole. So it's a super favorable downhill reaction right here at the beginning of the TCA cycle. All right. And so the reaction we're essentially looking at here in this condensation reaction, if you sort of want to get a slightly more detailed view of it, and we're going to take this in some stages here, right? So essentially we got a situation where we're going to basically abstract one of those protons from that methyl group on that acetyl group. And we're going to create, when we do that, we're going to create an enol, a reacted enol, that we're going to condense then with that carbonyl carbon. So essentially what we're running here is a mixed Claisen aldol condensation. And then once that's done, we're then going to hydrolyze off that thioester bond. And that hydrolysis reaction is sort of what staples this thing in place, right? We make it really one way, massively energetically downhill by hydrolyzing that thioester bond. And so we're committed, right? So this, like I said, by virtue of this big downhill step that we take at citrate synthase, this is sort of the committed step. An acetyl group goes to this point in the TCA cycle, it's committed. It's in and it's going to go around the cycle, right? So this is that critically important initiating step. And we're burning some significant free energy here, right? Because we hydrolyze off that thioester bond, which means this enzyme can't miss, right? If it does, if it wastes that acetyl group and just generates acetic acid by hydrolyzing that acetyl-CoA, it's incredibly wasteful, right? So how on earth does the enzyme enforce this? How does it make this happen, right? All right, so let's look at the citrate synthase reaction in a little more detail. And there are a couple other things we need to think about in this reaction relative to this process of creating that enol and why this reaction is using a thioester instead of a classical alcohol ester, right? Okay, so let's take a look at that. All right, so here we are with the TCA cycle. We're going to skip over a little that. All right, so citrate synthase can't screw up, right? And it's going to do something. It's going to intentionally hydrolyze that thioester bond to get this reaction committed, to give us that big downhill run into the initiating TCA cycle. So how does that work? Well, there are a couple of things you might guess at based upon our discussion of certain types of enzyme mechanisms. And I'll give you a hint here. Here's citrate synthase. It's a dimer, symmetric homodimer. This version is, and I don't remember if this is mammalian or bacterial in terms of the structure. Here's one monomer here, sort of there's blue, there's one domain. Here's the yellow is another domain. And then there's symmetric dimer over here. The oxaloacetate binding site, remember that's the 4-carbon guy coming in. It's right here in this interface. You can see it sort of right there, right in between the two domains, right? Notice what happens when it binds oxaloacetate. Look what happens to the active site, right? Look what happens to the enzyme. The enzyme clamps down, right? Changes that conformation. There's that induced fit idea again, right? The binding of the substrate and the preparation for the reaction is coupled thermodynamically to a structural rearrangement of the enzyme in a really fundamental way. Two important things are going on here. One, this is dehydrating and I'm removing water from the active site, just like we saw for oxaloacetate. The second thing that happens here is the citrate synthase reaction is a sequential ordered bimolecular reaction. Remember that scheme? And you can imagine why that might be the case. For citrate synthase, the binding site in the active site for acetyl-CoA does not even exist in the open form of the enzyme. It's not even there. Oxaloacetate has to bind first before the binding site even exists for citrate synthase. So there's no way for CS, also called, to bind and accidentally hydrolyze acetyl-CoA before the other substrate it needs, oxaloacetate, is sitting there and ready to go. All right, so that's sort of a key idea for how this enzyme works. So let's take a look at the reaction a little bit. Like I said, the way this reaction is going to work, here's oxaloacetate. It's already in the active site. Enzyme's begun to close down. It's dehydrating. It's eliminating all that water, right? And now we've created the binding site for the acetyl-CoA. Here, acetyl-CoA is coming in there. And remember, like I said, the name of the game for this reaction is to remove that proton, right? Basically create a reactive enol here, right? So we pop that proton off, the electrons come down here. A little acid-base assist from a nearby histidine residue helps basically an acid, essentially that histidine, protonated histidine acting as an acid, protonates that nascent formation of that enol group to create the reactive enol we need. Now, I sort of raised this point of why do this with a thioester? Why go to, remember we went to all this trouble of making acetyl-CoA? Well, there are two reasons for making a thioester here instead of using a classic ester, alcohol-based ester. One, like I've said, we're going to see in a minute, the hydrolyzing that thioester helps make this reaction one way because that thioester is much less stable than an alcohol ester like we talked about last time, right? So pulling that pin at the end of this reaction really helps us stable this in place. But there's a second reason for doing this. This reaction, I just erased my notes, depends upon forming that enol by exploiting the acidity of those protons alpha to that carbonyl group. And guess what? Those protons are much more acidic if the group attached to the carbonyl is a thiol than if it is an alcohol, right? An alcohol ester, an oxygen. And that's because the resonance that would normally exist between the carbonyl carbon and an alcohol group here doesn't exist in the thioester. Because it doesn't exist, disrupting and forming that enol, pulling this proton and forming that enol has, you want to think about it, there's less for the molecule to lose. It's energetically way more favorable to do that if you're not going to disrupt resonance that would have existed in the ester, which makes this proton much more acidic in the thioester. That methyl proton, those methyl protons are much more acidic in the thioester than they are in an alcohol-based ester. All right, so that's sort of the reason, part of the reason for making acetyl-CoA to begin with. All right, so the base is thought to be an aspartic acid residue that helps pull that proton off to make that reactive enol, right? So once we do that, again, the histidine has been a little acid catalysis here. Here's our reactive enol. The histidine then reverses, acts as a Bronsted base, pulling that proton back off and helping direct the enol to attack nucleophilically that carbonyl carbon of oxaloacetate to form in the active site of the enzyme that sort of citriol-CoA, right? So that's how we synthesize that carbon-carbon bond to make the 6-carbon unit. But we're still sitting here with that thioester bond, and the remaining step, the reaction, is to position some hydrolytic residues that now clip that thioester and turn it into a carboxylic acid group. And that's that really key step the enzyme doesn't want to mess up. And those amino acids that run this hydrolysis don't even get positioned in the active site until citriol-CoA is formed. So the enzyme never screws this up and accidentally hydrolyzes acetyl-CoA to acetic acid. Okay, so that's the basic reaction of citrate synthase, right? So we can see how we did this, right? Let's go back for a second, however, and think about where we've come from and what we need to do. So a little forward-looking, thinking about the logic, what we've done. I sort of explained why we have a thioester here, why we went to the trouble of making the thioester, why it's important for the acidity of that methyl proton to run this Claisen-Aldol condensation, 1. 2, we need it for the free energy to make this thing essentially one way. All right, but remember, if you think back to my sort of bird's eye view, the goal of phase 2 of the cycle is to basically kick off a bunch of carbon dioxide and suck out a bunch of those high potential electrons from the structure of citrate. All right, specifically, the carboxylate groups we're going to get rid of are that guy and that guy, right? We're about to basically run some reactions that are going to eject those carboxylate groups as CO2, right? Question is, if you look at that molecule, how do you do that? I mean, it's not obvious at all. Carboxylate groups just don't spontaneously fall off the organic molecules they're incorporated into. You got to provide a driving force of some kind that makes that CO2 a good leaving group. And we've seen 2 examples of that, right? Think back. The first example I showed you guys was in my general discussion of sort of like, different types of catalysis. And we talked about covalent catalysis, and we talked about decarboxylation of beta keto acids, right? When a carboxylate group was 2 carbons away from a carbonyl, like a ketone, right? Second example, we talked about decarboxylation of alpha keto acids. We just talked about that last time, right? The decarboxylation of pyruvate, remember, to form acetyl-CoA. Took a cofactor, we had to have that stabilized TPP carbanion, but the reaction was doable if we had we'd have a carbonyl there that we could then come in with TPP and create that stabilized carbanion, that hydroxyethyl TPP group. But as long as we had a carbonyl there, we could make this happen. Same for that beta keto acid reaction, if you remember back, right? All right, well, look at citrate. What do we have to work with, right? If you look at that molecule and just think about the logic of what we need to do, if we could create a ketone group somewhere, we could potentially think about ejecting those CO2 groups. And what do we have to work with? Like here, we have an alcohol. So the logic of the next part of this pathway then is to take that alcohol group and move it over. And specifically, we could move it here, right? Or we could move it here. And we'd make, if we move it here, we would make this group, this carbonyl group, carboxylate group here, that'd be beta, right? Here's alpha, beta, right? And then we'd have an alpha carboxylate group here. Hey, now we got something to work with. But we could do that over here with my little marked carbon too. Molecule's kind of symmetric, right? Turns out the next enzyme that's key for running this reaction only goes one way. It only moves that alcohol group to that carbon, I guess, the opposite side of the molecule from the two we just brought in from acetyl-CoA, right? And we'll see that in the next reaction.